All right, we're just gonna start. So I'll share the screen. And you guys can both hear me and see the textbook, right?
Yeah,
Okay, awesome. So last class we ended over here at 333. We were just looking at these push button interlocks and these reverse circuits over here. We're gonna start at 15-4, which are gonna be the applications of magnetic reversing starters. And again, if we get disconnected, I'll just restart the Zoom session. If anybody joins and I don't catch them, just let me know. So as we discussed last time, we have limit switches and indicators, right? If you ever have an indicator for anything, you're going to put it in parallel with the coil that it's trying to indicate is on, right? So if you have power going to the F coil or the forward coil, then you want power going to the L light or forward light, right? So the forward light will always be on whenever the forward coil is on. And in this way, you'll always be able to tell if something is going forward or backward or reverse without actually seeing the thing move. It's useful in many different applications. So we're generally used to just seeing a light come on when something happens, right? But let's say power is either gone or the voltage decreases by a lot and our motor stops moving. It still has power. Let's say instead of 240, something happens and it's got 100 volts on it. So there's still power, but it's not enough for you to see any movement. And so nothing's moving. You just assume there's no power. So you go and you say, hey, what's going on with this motor? What's going on with this equipment? You get close to it. You try to see what's up with it. You try moving it around, and the power just comes back on. And all of a sudden, you're very close. Your hand's right in the middle of some very large piece of machinery that's moving, or a blower motor, or anything else that could have very dangerous consequences. In this way, we always have indicator lights. We'll have one for forward, one for reverse. You may have one that's just active in a different part of the facility or wherever you're working. So in general, these will always be useful, even if you have less voltage than the motor would require to actually operate. Sometimes these will be dimly lit and you can tell there's still power. In other cases, well, that's a very good use case for them, right? If there's not enough power or enough voltage to actually let the motor work, the lights will still work until, the voltage goes down by a lot. So that's the indicators going on to the limit switches. They're called over travel switches. And the reason is so that these motors right here, whatever motor that these contactors are controlling, don't over travel, right? So if you have a motor, let's say going to a garage door or going to a conveyor belt or anything like that, and there's some hard limit, right? So you can't open a door past a certain point or close it past a certain point. Likewise, if you have a conveyor belt that's not continuous, so it doesn't loop back on itself, it may be the case that there's a point in which you have to stop, a point in which you have to start, or if something rotates, right? You'll have 360 degrees of rotation or 180 degrees of rotation. At which point, if you want to keep going, you'd have to go back in the other direction. You'd have over travel or limit switches there to prevent any action where the motor's moving past where it's supposed to. So how do we put these into the circuit? We have our normal circuit. We have our holding contacts. We have our coils, our indicator lights, our stop and start buttons, whatever you have. These would go in series with the line that's going to the forward and reverse coils, or whichever coil corresponds to the contactor that corresponds to whatever is actually controlling your motor. So in this case, let's say this normally closed switch is on the floor, for example. And if you have a garage door, let's say as soon as your garage door closes all the way, its bottom is going to hit the floor, right? And this switch is on the floor, so the door is going to hit the top of the switch. And once it hits the top of the switch, it's going to open the switch because the switch is normally closed. So when you actuate it, it's going to open. In this case, this part of the circuit opens. And so the forward coil is de-energized. The forward contact opens, which prevents the forward direction on the motor from actually getting any power, which stops that motor or the door from closing past where it's supposed to close. The opposite and same is true for reverse, right? So forward, reverse, they're the same circuit, just for different operation. So this is something that we saw last time, or last class we discussed this not so in depth, but we did discuss it. I'll just quickly go over it. Limit switches for controlling reversing. In this case, you can see that you have your CR coil. This is the control relay, right? So control relay's coil right here. It has two contacts. One, we can see that this is very familiar, right? Whenever we have this, it's just a holding contact. So you press start, energizes, closes, and it stays held, which means as soon as you press start, this closes and it'll just stay closed until you press stop or you remove power. So you press start. Now this entire section has power. You have a forward coil and the forward contact, a reverse coil and the reverse contact, as well as these interlocked limit switches. So when one is open, the other is closed. In normal operation, we can see that if CR is closed, power will go through here, and power branches into these two circuits. We know that this is normally closed, so a normal operation, power is going to go through here. It's going to stop over here because it's an open circuit. And the reverse contact is normally closed, so it's going to allow power to go through, as we saw here. It's an open circuit, so the coil is not energized, so this will stay closed. And then the forward coil is going to get power, which means forward here opens, and the forward contactor will actuate, which causes the forward motion to occur. So your motor is going to move in the forward direction. Let's just say, again, the example of a door. So your door is closing, your garage door is closing, and it's gonna keep closing until it hits the limit. Once it hits the limit, this is gonna open and this is gonna close, right? So the normally close opens, normally open closes. In this case, well, reverse, we're not even gonna look at this part, right? Because this opens, we know that this path can no longer get any power at all. So we're gonna look down at this path. This path is normally open, but we hit the limit, so it's gonna close. It closes, we allow power to go through here. We said this is no longer energized, so this is normally closed. It's not gonna do anything because this is not energized, so it's gonna stay closed. So power is gonna go through this, it's gonna go through this, and it's gonna hit the reverse coil. So the reverse coil is gonna be energized and the reverse contacts are gonna be active, which is gonna cause the reverse action to occur. Now, if this specific limit switch is a limit switch where if you press it, it will reverse its orientation. So it's going to hold these to the opposite state. And if you release it, it'll go back to its normal state. What's going to happen is it's just going to back off a little bit and repeat the cycle. But if this limit switch is the one that latches, so for example, if the door closes all the way, these are going to reverse direction, even if the door opens a little bit. And the only way to get back to its original state is for the door to open all the way and hit its other limit. So there's going to be one limit switch on the floor, one limit switch all the way up top where the, so garage doors, you know how they curve back up into the actual garage? So all the way back where you have the actual motor, there might be another limit switch. So when the door opens all the way, it'll hit that limit switch, right? And they're interlocked, meaning it'll only change state when one of them gets hit. So even if the door closes all the way, it'll change state, but if it opens back up, it's not going to revert state. It'll only revert state when the door opens all the way. And what that would allow, so this wouldn't be a very practical circuit, because what this circuit would do would make it so that the door would close all the way, hit these limits, reverse their position. And since these are identical circuits, you can just imagine that forward motion, if we reverse this, would equal reverse motion, right? So door closes all the way, hits the limit, and then it opens all the way, hits the limit, then closes all the way, hits the limit, and opens all the way, and hits the limit. So in this specific circuit, what you're doing here is just oscillating, right? So it's not very practical for a garage door because you'd just be going open, close forever. Now, the next way to use limit switches. So in this case, we're using the limit switches in the latching form so that we can control the reversing. In this case, we just want to protect our motors. We want to protect our materials, anything that's moving, right? Anything that's mechanical is going to be stressed by too much pressure, too much force being applied on it. So this is going to be protecting that. And these are over travel protection. So in this case, we can skip some of this, right? So our stop button, as well as forward reverse, which is like the start button. We have our coils and the respective contacts. So F coil, F contact, R coil, R contact. And so these would be like holding contacts. So you press forward, energizes, closes, it'll stay energized, right? So it'll keep going forward. In addition, we have the reverse normally closed and the forward normally closed over here so that if you have forward energized and your motion is going forward, so whatever your equipment is going in the forward direction. Um, uh, Reverse is normally closed, which is going to allow the current to keep going, and forward is energized. So this normally closed will open, and regardless of whether you press or not, this is going to be open, and so you can't get any power at the reverse coil. Now you have these over travel protections. So in this case, we said the door is just going to keep opening and closing, and these latch, right? So these are not going to deactivate as soon as the door gets open enough to no longer hit the limit. In this case, however, if the door closes all the way, it's going to hit the forward limit, which is going to open this and stop the motor from going any more forward, right? But as soon as it backs off a little bit, this is like a momentary contact. So as soon as the motor causes the door to open just enough, maybe like a couple millimeters so that the switch is no longer pressed, this will close back and normal operation will occur. Usually, so in this particular example, if the door closes all the way, this limit is hit, so it opens, right? Now, when this opens, what happens? This contactor, this coil right here is going to be de-energized. So when it gets de-energized, this is going to open back up. So it's not just going to open a couple millimeters, and then as soon as the limit switch is closed again, it's going to close back, open, close in a very small distance. So since this is a latching circuit, as soon as this opens, as soon as the limit situation occurs, it's just going to open this contact, and it's going to be the case that you have to press forward again to latch it back. So in this case, this is more representative of what we discussed about the elevator doors in last class. Okay, so selector switches for determining direction of motor travel. In this case, realistically, this circuit right here is exactly what this circuit is. It's exactly what we saw at the holding circuits. It's just oriented in a different way, and it doesn't have these limit switches. So if we look at it, okay. So if we look at it, we see overloads on the motors, on the coils. So that's perfectly fine. If an overload trips, you should open and not allow anything to happen. We have our forward coil, reverse contact, normally closed, forward contact, normally closed. So if forward is energized, this forward contact will open and it will not allow the reverse coil to be energized, and vice versa. So if reverse is energized, this opens, which will never allow forward to be energized. And in that configuration, you can never have forward and reverse at the same time, which would cause a short circuit. If we go back, we saw that in these holding contacts, in these holding circuits right here, we said that if F is energized, then this F normally open is going to close, which is going to keep everything running, right? In this case, let's say our selector switch is in forward, and you can pretend like it's just a wire going from this point to this point. Let's actually assume reverse because that's what the diagram shows, so it'll be easier to visualize. Let's say we're in the reverse direction. The stop button is not open, so it's going to allow power to go through. You press start, so now start conducts. and this is just a switch. We have it in the reverse position, so it's going to conduct down here. We're not going forward, clearly, because this is open. So this is going to stay closed because it's normally closed. And the reverse coil is going to get energy. So the reverse coil gets energized. And if we look, so this is going to open, which again, nothing was going to change because it didn't have power anyways, but this opens. And then this contact, which is normally open, this reverse contact is going to close. So now once it closes, well, even if you let start go, power will go from stop. It'll go and take this branch. This is now closed because R is energized. It'll go back through here. It'll go through this switch and it'll keep R energized. So the R coil will always remain energized, as we saw before in the latching or memory circuits. If we flip this switch to forward, and have in mind, you never want to flip from reverse to forward on a motor. You always want to give the motor some time to slow down to a stop, or at least close to a stop. This way you don't get massive current spikes, and of course damage to your motor and equipment. So let's say we switch this to forward. The same is going to happen, except everything is just reversed, right? So I'm assuming you guys can see that. You press start, energy to forward. This is already closed because it's normally closed. Energized, closed. So now even if you let start go, goes to stop, through the forward contact, through this switch, the selector switch goes to forward. Reverse is not energized, so this is going to stay closed, and forward stays energized. So it latches to forward now. So in this circuit, it's exactly as you see in this circuit, minus the limit switches, and just a simpler way to see it. And of course, instead of having a forward and reverse button, you just have a start button and a forward and reverse switch. And over here, the only addition would be you have a couple components down here. So the start button goes from 2 to 3, right? So start right here, 2 to 3. That's just bringing it down. You have the forward light indicator, goes from 6 to L2, which is 6 right here to L2 right here, which is in parallel with the forward contact, with the forward coil, as well as the overload protection. And the reason you want it across both the coil and overload protection instead of just having it in parallel with the coil is because if an overload occurs, you're actually going to have this light turn off, right? So if instead of it connecting to L2, you connect it just to this end, this overload opens, and so now you have an open circuit from this side of the light and L2, which means the circuit can't be completed. So now if an overload situation occurs, it'll just look like everything's off. You want it to be such that your motor turns off, but your light showing that you have forward selection stays on. Again, for safety, you want to make sure that everything is actually off. You don't want to assume that you don't want to assume that power is gone, right? So you may have an overload situation. You still have power, but the motor's internal overload is just, or it could be an external overload. It just tripped. So now you just have to wait until it cools back down to allow circuit operation again. So you don't want to assume you don't have power. With going from 6 or the left side of these coils, right? So again, forward and reverse lights are exactly the same. One just goes to the left side of forward coil, one goes to the left side of the reverse coil. But basically, even if the forward and reverse coils are not energized, you still want to know, is the start button closed and am I in the reverse or forward position? Because if you know that these lights are on, you know that there's still power. There's still power at the motor. There's still power. Well, there's not power at the motor, but you'll have power at the starting contactor. So you know there's still power, and you're just going to be worried about that because let's say these lights are off and you just assume there's no power. You go to your equipment, you start working there, and the overload cools down and it goes back to being closed. And now your motor starts with your hand right next to it, or worse. So now we have selector switches in jogging control. And by jogging, if I can jog your memory, apologies for that, but okay, so jogging, what that refers to is instead of just pressing forward or reverse and just having it go, just you press forward and you let go and you walk away and it just keeps going forward. Jogging refers to you pressing forward, motor moves forward. You let go of the forward button, motor stops moving forward. You press reverse, motor moves reverse. You let go of reverse, motor stops moving in reverse. So it removes the latching feature. And run, of course, is just normal operation, which will make it normally operate. So when you press forward, it'll keep going forward until you stop, until you either press stop or remove power. Again, if we run out of time, which we will in about 10 minutes, just rejoin the Zoom session and I'll take a quick minute to see if anybody else joined the call. Okay, we have a couple more. Okay. All right. So moving on. So jog and run. So how does this circuit work right here? We have a selector switch, which either switches between right side of stop to this run contact, which just goes into here, or the jog contact, which literally just connects to nothing. It's like you disconnecting here. So instead of thinking of a selector switch, you can think of how does the circuit work if I have a jumper from this point to this point, and how does it operate if I remove that jumper from this point to this point? So let's analyze this real quick. Overload, we know what that does. It's going to be on the right side of our coils. We know what those do. Reverse coil, reverse contact, forward coil, forward contact. Can't have them on at the same time. So that's what these contacts do. We have the interlocked forward and reverse buttons. So let's assume stop is closed. Current goes through here. You press forward. It's going to close the circuit. So your power is going to approach the forward coil. At the same time, it's going to break this point. So there's no way that power can approach the reverse coil. Likewise, if you press reverse down here, it'll allow power to go through to the reverse contact while making it impossible for power to go through to the forward contact because it opens the connection over here. So, okay, so that's our forward and reverse switches and they're interlocked. What else do we have to analyze? The stop button, if you press it, it opens the circuit, nothing's going to happen. So the only thing we have left is this forward normally open contact, this reverse normally open contact, as well as this selector switch. So what would happen if we just had a wire going from here to here? It looks like we have one of those auxiliary contacts going across the forward switch, an auxiliary contact going across the reverse switch, right? If we had a wire just going here, this connects down up to here, goes down, right? Left side of reverse switch, and the right side here is on the right side of reverse switch. So this is very similar to the holding contacts. Reason is they are holding contacts. So if you have it in run operation, these will act as holding contacts and it'll operate exactly as we've seen before. If you have it in the jog operation, however, it's going to be the same as breaking the connection right here, breaking the connection right here, so that even if the forward coil gets power and the forward contact closes, well, there's an open circuit here. So as soon as you let forward go, it's going to have an open circuit here, and you have an open circuit here. So now there's no more power going to your forward coil. And because of that, you just have your entire circuit off, right? So there's nothing happening anymore. So that's what this selector switch does for jogging control. You can either have it in run. I want my motor to keep going forward until I press reverse or until I press stop and I press reverse and vice versa. I want to keep going in reverse unless I want it to stop. In this case, I may want to put it in inspection mode. I may want to, you may have like a crane, for example. In a crane, you don't want to just press forward and let it keep going until you tell it to stop. No, you want to make it so that if anything happens, let's say you're pressing forward and you collapse, right? So let's say you black out. Well, the forward is going to keep going, that crane is going to keep moving, and you may kill people, you may cause extreme damage to the buildings, you may destroy the crane. So very, very dangerous. You want to make it so that even if you were to collapse from pressing forward, you're pressing forward, crane's moving. If you were to collapse, well, you stop pressing forward because you're on the floor now. And so the crane stops moving. So for safety, this is very important. Another reason is it's important is because if you're moving something like a crane or even something very small and you need precision, you don't want to make it so that it's just going to keep moving one direction until you press the other direction or until you press stop. No, you want it to be very precise. So you want it to you want to jog it towards where it's going. You don't want to run it to where it's going. And that's where the terms jog and run come from. Making sense so far?
Yeah.
Thank you. Okay, so now it's going to be motor control wiring methods. There are four different methods. You have direct hardwiring, so everything's connected directly. You have hardwiring using terminal strips, so everything's connected directly inside the equipment, but at the end, wherever you have to interface, whether it's the area you're gonna connect your thermostat to, or you have some external controller or anything like that, there's gonna be a terminal strip. So you have your equipment, terminal strip, then you have your controller, terminal strip, and you wire everything through terminal strips. And PLC wiring, which we're not going to go into in this chapter. PLC wiring is where you have a PLC or a programmable logic controller between your equipment and your inputs. So Open may not just send power to something. Open may send a signal to the PLC, and the PLC does 100 million different things, and then it controls the equipment. And then you have electric motor drive wiring. So the PLC and electric motor drive, we're not going to discuss in this chapter. We're going to discuss that maybe in a future lesson. And yeah, so I'll go through direct and the terminal strip connections. So the first one is the electric connections for direct hardwired circuits. And in this case, within the equipment, within the controller, within everything inside the circuit, we have a wire going from this point to this point, a wire going from this point to this point, as well as some junction over here, maybe a wire nut or something else, going from this point down here, from this point to here. So we have a wire going to every single part. And without exception, even if you have a cable coming out of your equipment to some controller, there is no terminal strip. That cable literally runs. Every single wire that's in that cable runs from the circuit board or from the direct connections of the switches in your controller in through the conduit and then into your equipment, like directly, for example, directly to the motor. It would be an extreme example, but let's say your open switch has one wire soldered or crimped onto one lead, runs through everything, and then it connects directly to the motor. So you can imagine that would be extremely annoying to troubleshoot. It'd be extremely annoying to modify it, as well as test or anything like that. Why? Because now if you want to test something, you have to scrape off the wire, you have to cut the wire just to get some metal contact for you to put your probes on. And as we know, then you'd have to repair everything. So very annoying. So here's an example of this just brought up into an actual circuit. This is an example of direct connections. So you can see that the switches inside this control box is, connected directly into wherever they go inside of the circuit. So very annoying. So if you have a contact over here, you're literally only one wire away from here to your actual controller. So if you don't have the wiring diagram, good luck because you're going to have to trace every single wire by hand and you have to get very lucky as to not mess anything up. So for example, you can have like a low voltage signal right next to a 240 volt line. And if you're trying to cut something so you can measure it, you'll either get shocked or you'll cross wires and you'll break something. Okay, so I'm gonna stop Zoom right now and I'll just restart it.